The Silurian hypothesis begins with a bold and unsettling question. Could there have been an advanced civilization on Earth long before humans ever walked the planet? At first glance, the idea might seem like something pulled from a work of speculative fiction, but its origin and intent are rooted firmly in scientific inquiry. The hypothesis takes its name from the Silurian period, a span of geologic time roughly 443 to 419 million years ago, long before the age of dinosaurs and unimaginably earlier than the appearance of Homo sapiens. Despite this connection in name, the hypothesis does not claim that advanced life existed during that period, nor that evidence of such life has been found. Instead, the name serves as a thought-provoking reference point, a reminder of just how vast Earth's history truly is. The underlying concept is simple to state, but incredibly complex to investigate. If an industrial or technological civilization had arisen in Earth's distant past, millions of years before humans, would any evidence of its existence still remain today? And if so, would we even know how to recognize it? On the surface, it may seem like a straightforward matter of finding artifacts, ruins, or other unmistakable signs of advanced activity. But the reality is far more challenging. Earth is not a static archive. It is a dynamic, ever-changing system where wind, rain, volcanic activity, tectonic shifts, and biological processes continually reshape the surface. Over the span of millions of years, even the tallest mountains can erode into plains. Entire ocean basins can close and reopen, and the continents themselves can drift thousands of kilometers from their original positions. Given these immense timescales, the Silurian hypothesis asks us to confront an uncomfortable truth. Perhaps our own civilization, with all its skyscrapers, satellites, and sprawling cities, might also vanish almost completely if given enough time. Human structures, even those built of concrete and steel, are fragile compared to the geological forces at work over millions of years. If an equally advanced or even more advanced civilization had once thrived on Earth but disappeared tens or hundreds of millions of years ago, the traces they left behind might be so eroded, buried, or transformed as to be indistinguishable from natural formations. The motivation for this hypothesis is not purely about rewriting Earth's history. It is a scientific thought experiment designed to sharpen our understanding of planetary processes and the persistence or fragility of evidence over deep time. By exploring this possibility, researchers can refine the methods used to detect signs of past civilizations, not just on Earth, but on other worlds as well. In doing so, the Silurian hypothesis bridges multiple disciplines, including geology, paleontology, archaeology, and planetary science, creating a framework to consider the longevity of technological markers and the kinds of clues that could survive the relentless march of time. This line of inquiry also intersects with astrobiology, the study of life in the universe. If Earth could, in theory, have experienced more than one technological civilization over its long history, then other planets, especially those that have existed for billions of years, might also have gone through multiple cycles of rise and collapse. It is a humbling and slightly haunting notion. We may not be the first intelligent beings to leave a mark on our home world, and even if we are, our own mark may not endure forever. Our industrial age has been underway for barely 2 centuries, yet we often think of it as permanent. The Silurian hypothesis reminds us that permanence is an illusion on geological timescales. To take the idea seriously, scientists must strip away the assumptions and biases that color how we interpret the fossil record and the geological archive. When we examine rocks from the distant past, we look for fossils of life forms, traces of climate change, chemical signatures, and evidence of planetary events like asteroid impacts or massive volcanic eruptions. But the hypothesis encourages us to ask a different kind of question. Could some of the anomalies we find, chemical spikes, unusual sediment layers, isotopic shifts, be the remnants of industrial activity from a lost civilization? This is not to suggest that we have found such evidence, but rather to recognize that without asking the question, we might not even know what to look for. A key element of the Silurian hypothesis is its acknowledgement of how easily nature erases the past. Biological material decays rapidly, metals corrode, and complex materials break down into simpler compounds. Plastic, one of humanity's most enduring creations, might persist in the environment for thousands or even millions of years under certain conditions. But over geologic timescales, even it will fragment into microplastics and eventually degrade. In the far future, the distinct chemical fingerprints of today's industrial activity, such as elevated levels of carbon isotopes from burning fossil fuels or synthetic compounds never before found in nature, may be among the few clues left to tell the story of our existence. The choice of the Silurian period as the hypothesis's symbolic namesake serves another purpose. It reminds us that complex ecosystems have thrived on Earth long before humans, and that life has rebounded after mass extinctions in ways we are only beginning to understand. If intelligence is not unique to humans, and if it can arise under the right environmental pressures, then perhaps it has done so more than once. In such a case, our current civilization could be part of a repeating pattern rather than a singular event. This prospect forces us to consider the implications not only for our understanding of Earth's past, but also for our expectations about the future of intelligent life in the cosmos. Furthermore, the hypothesis urges a kind of scientific humility. The absence of evidence is not evidence of absence, particularly when the evidence in question would be competing against hundreds of millions of years of erosion, subduction, and metamorphosis. A civilization's architectural feats might crumble, its technology might corrode, and even its largest monuments might be ground to dust by glaciers or buried under sediment. What might endure instead are subtler signals, chemical residues in soil and rock, unexplained mineral deposits, or isotopic anomalies hinting at artificial processes. Learning to identify such markers is essential, not just for understanding Earth's potential hidden history, but for expanding our search for extraterrestrial civilizations that may have long since vanished. In exploring the Silurian hypothesis, scientists also confront philosophical questions about the nature of civilization itself. What does it mean for a civilization to leave a lasting mark? Is permanence measured in centuries, millennia, or millions of years? Are technological societies inherently fleeting, their achievements destined to be swallowed by time? If we imagine a pre-human civilization, we must also imagine its end, whether by environmental collapse, cosmic disaster, or self-destruction. And in imagining that, we inevitably reflect on our own vulnerabilities as a species. Ultimately, the Silurian hypothesis is less about proving that a pre-human civilization existed and more about refining our ability to detect one if it did. It challenges us to think beyond the narrow slice of history we occupy, to stretch our perspective across hundreds of millions of years, and to recognize the vastness of Earth's story. It is a call to curiosity, urging us to look deeper, think longer, and question more boldly. Whether or not the hypothesis ever yields evidence of another civilization, it enriches our understanding of how time and nature shape the traces of life, and reminds us that even the most advanced societies may one day be reduced to whispers in the geological record. The Silurian hypothesis, while captivating in its premise, did not emerge from a vacuum of wild speculation or unfounded fantasy. Its origins trace back to a serious scientific inquiry published in 2018 by two highly respected researchers, Gavin Schmidt, a climate scientist and director at NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist at the University of Rochester. The two were not attempting to prove that an advanced civilization existed on Earth before humans, nor were they making any extraordinary claims without evidence. Instead, their goal was to engage in a rigorous thought experiment, one that would challenge both scientific methodology and the assumptions we hold about our planet's deep past. This thought experiment sought to answer a seemingly improbable but scientifically relevant question. If there had been an industrial or technological civilization on Earth millions of years before humans, would we be able to detect its existence today? To ground the hypothesis in an approachable framework, Schmidt and Frank chose to give it a memorable name, the Silurian Hypothesis. This choice was inspired by a fictional alien race from the long-running British science fiction series Doctor Who. In the show, the Silurians are portrayed as a highly advanced reptilian species that evolved on Earth during the Silurian period, long before the rise of humans. The scientists' use of this name was not an endorsement of the show's storyline or a literal claim that such beings existed. Instead, it was a playful nod to popular culture, helping to draw attention to the core idea while keeping the discussion firmly in the realm of scientific plausibility. This light-hearted reference belies the seriousness of the scientific challenge they posed. How resilient is evidence of civilization over geological time, and what signatures would survive long enough for a future species, or even alien visitors, to find? The historical context of this hypothesis is grounded in humanity's ongoing exploration of planetary science, climate change, and the geological record. We live in an era where human industrial activity is leaving a measurable mark on the Earth, what many scientists call the Anthropocene. Our burning of fossil fuels, large-scale agriculture, industrial pollution, and extensive urbanization have all altered the planet's atmosphere, oceans, and land in profound and measurable ways. These changes include increased levels of greenhouse gases, the spread of synthetic materials like plastics, and the presence of unusual isotopes from nuclear activity. If humanity were to disappear tomorrow, many of these changes would persist in the geological record for tens of thousands to millions of years. The key insight from Schmidt and Frank was to invert this observation. If our civilization can leave behind such traces, might another long-forgotten civilization have done the same? And could we recognize it in the geological archives? The Silurian hypothesis also rests upon a deeper understanding of Earth's natural history, which is defined by cycles of emergence, transformation, and destruction. Over the planet's 4.5 billion-year history, life has repeatedly flourished and been wiped out by mass extinction events. These extinctions, such as the end Permian event about 252 million years ago, or the asteroid impact that ended the reign of the dinosaurs 66 million years ago, reset the evolutionary clock, creating opportunities for new forms of life to emerge and dominate. In between these cataclysms, entire ecosystems evolved and vanished, without leaving behind detailed fossil records for every organism that ever lived. The fossil record is notoriously incomplete, shaped by the selective processes of preservation, erosion, tectonic activity, and sedimentation. Organic remains often degrade rapidly, and even hard structures like bones or shells may fail to fossilize unless conditions are perfect. Over millions of years, the movements of Earth's crust through plate tectonics recycle the surface, subducting old seafloor into the mantle and uplifting new mountain ranges. This constant geological churn means that direct evidence from deep time is incredibly rare. By highlighting this reality, Schmidt and Frank were emphasizing that the absence of evidence is not necessarily evidence of absence. The further back in time we look, the more challenging it becomes to reconstruct a detailed picture of the biosphere, let alone detect traces of a civilization. If humanity's cities, infrastructure, and artifacts were somehow erased by tectonic recycling, glacial erosion, and chemical weathering over millions of years, would anything be left to testify to our existence? This question becomes even more pressing when one considers that most modern materials are not designed for geological permanence. Concrete structures might crumble within tens of thousands of years, metals would corrode and oxidize, and most plastics, though they could persist for millions of years in some form, might be broken down into microplastics indistinguishable from natural particles in ancient sediments. The implication is that even a global civilization could vanish from the physical record under the right conditions. The choice of the Silurian period as part of the hypothesis's title was also a subtle way to provoke thought about the scale of time under consideration. The Silurian period, which lasted from about 443 to 419 million years ago, was an era of significant evolutionary milestones, including the diversification of jawed fish and the colonization of land by plants. However, it predates the appearance of complex terrestrial ecosystems with large animals by hundreds of millions of years. By naming the hypothesis after this period, the scientists implicitly acknowledged that the concept was not tied to a specific historical claim, but was instead a lens for examining Earth's entire geological record, stretching from the distant past to relatively recent prehistory. It was about fostering a mindset that could be applied to any period of Earth's history, where a hypothetical technological species might have arisen and then disappeared without a trace. This framework also challenges anthropocentric thinking, which tends to view humanity as the pinnacle and sole possessor of technological intelligence on this planet. While there is no evidence today for a pre-human technological species, the Silurian hypothesis invites scientists to confront the possibility that our species is just one of many that could have reached industrial capability over the course of Earth's long history. It draws on parallels from astrobiology, where researchers consider the possibility that multiple civilizations might have arisen and fallen on planets orbiting distant stars. If such cycles can happen elsewhere in the universe, why could they not, in theory, happen here? The 2018 paper also emerged at a time when advances in analytical technology and planetary exploration were providing new ways to detect subtle signatures of environmental change. From ice core sampling to deep-sea drilling, scientists have become adept at reading the layered archives of Earth's past. This skill has been essential in reconstructing past climate shifts, ocean chemistry changes, and extinction events. The Silurian hypothesis takes this capability one step further, suggesting that we might also look for industrial fingerprints in these records. These could include unusual isotope ratios caused by synthetic chemical production, abrupt changes in sediment composition from large-scale mining, or spikes in atmospheric CO2 and methane unrelated to natural causes. Importantly, Schmidt and Frank's discussion was not an indulgence in pseudoscience, but an exercise in scientific humility. They acknowledged that no such evidence currently exists for a pre-human industrial civilization, and they clearly distinguished their thought experiment from claims made by fringe theories or speculative archaeology. The purpose was to sharpen the tools of detection and to remind the scientific community that our current understanding of the geological record is shaped not only by what is preserved, but also by the biases we bring to interpreting it. If we do not look for certain patterns, we may never find them, even if they are there. The historical background and origin of the Silurian hypothesis are deeply rooted in legitimate scientific curiosity and a willingness to explore uncomfortable possibilities. It emerged from the collaborative thinking of two scientists with expertise in climate science and astrophysics, who sought to connect lessons from Earth's environmental history to broader questions about civilizations in the cosmos. By framing the hypothesis in a way that is both accessible and thought-provoking, they succeeded in opening a new line of inquiry that blurs the boundaries between planetary science, geology, archaeology, and astrobiology. The Silurian hypothesis is not a declaration of hidden truths, but an invitation to think more expansively about time, evidence, and the fragility of civilization in the face of the planet's vast and often destructive geological processes. It asks us to reconsider how confident we can be about the uniqueness of humanity and challenges us to refine our methods for detecting not just alien civilizations on distant planets, but potentially forgotten chapters in our own planet's story. Over the vast expanse of geological time, Earth has undergone continuous cycles of transformation so profound that they could effortlessly erase almost every trace of a civilization, no matter how advanced it might have been. The processes at work, plate tectonics, erosion, volcanic activity, and climate shifts, operate over millions of years, reshaping the surface again and again. To fully grasp the implications of the Silurian hypothesis, one must understand that our human history, stretching back around 10,000 years of organized civilization, is barely a blink in this immense timeline. In the language of geology, this period is so fleeting that if the history of Earth were condensed into a single day, the entire existence of agriculture, cities, and technology would occupy only the last fraction of a second before midnight. Plate tectonics is one of the most effective erasers of surface evidence. Continents drift, collide, and split apart due to the movement of tectonic plates, a process that can recycle entire stretches of crust back into the mantle over tens or hundreds of millions of years. This means that the land on which any potential pre-human civilization once stood may no longer even exist as a stable surface. It could be buried miles beneath the ground or have been entirely subducted beneath another continent. Even areas that avoid complete subduction face constant erosion from wind, rain, and ice, gradually grinding down exposed materials into sediments that are carried away and redeposited elsewhere. The result is a geological palimpsest, new layers written over old ones, making it extraordinarily difficult to identify and interpret traces of the distant past. Volcanic activity compounds the problem. Major eruptions can bury landscapes under thick layers of lava and ash, preserving some materials in situ, but often destroying surface-level structures outright. Over time, these volcanic deposits become part of the rock record, indistinguishable from other geological formations, unless something highly anomalous, such as unusual chemical residues or isotopic signatures, remains within them. Similarly, meteorite impacts, earthquakes, and tsunamis can radically alter terrain, further fragmenting and dispersing any potential archaeological remains. Fossilization is itself a rare and selective process. Organic materials, like wood, cloth, or food, decay quickly without specific conditions such as rapid burial in an oxygen-poor environment. Even robust materials like metals and concrete eventually degrade. Metals corrode, ceramics fracture, glass weathers, and plastics photodegrade or break down chemically, especially over the spans of millions of years. For example, modern reinforced concrete, if left untended, might last a few centuries before crumbling into rubble, which would then be eroded and dispersed over millennia. While some materials like gold or certain alloys are more resistant to corrosion, their survival over tens of millions of years without complete loss is improbable, especially when subject to burial, water infiltration, and geological compression. Adding to this challenge is the fact that Earth's surface has been repeatedly reorganized through mass extinction events and continental rearrangements. At least 5 major mass extinctions have reshaped the biosphere, each dramatically altering ecosystems and leaving only scattered fossil records. These extinction intervals often coincide with large-scale environmental changes, massive volcanic outpourings, asteroid impacts, or abrupt climate shifts that could obliterate the physical remains of any complex society. The end Cretaceous extinction, for example, caused by the Chicxulub impact and subsequent volcanic activity, not only wiped out the non-avian dinosaurs but also reset ecosystems globally, potentially burying or vaporizing anything on the surface. Even if some physical remnants of an ancient civilization survived initial destruction, the process of sedimentation would eventually conceal them under layers of rock and soil. Over millions of years, these buried layers would be compacted into sedimentary rock, locking away any artifacts so deep that without deliberate drilling or mining, they would remain inaccessible. However, because mining and drilling today rarely reach more than a few kilometers into the crust, and even then only in specific locations, vast swaths of the ancient geological record remain unexamined. The overwhelming majority of rocks from earlier eras are located far beneath the surface, or have been altered beyond recognition by heat and pressure. The comparison to human civilization is striking. Modern cities cover large areas, but their physical footprint relative to Earth's surface is minuscule, and even the most iconic monuments would vanish quickly without maintenance. Roads would crack and be overtaken by vegetation within decades, steel would rust away in a few centuries, and entire skylines would collapse into dust given a few thousand years of neglect. After 1,000,000 years, only the most unusual and geologically stable circumstances could preserve even fragmentary remains. Now multiply that timescale by tens or hundreds of millions of years, and the probability of finding intact, recognizable artifacts approaches zero. What would remain instead are indirect markers, geochemical signatures, isotopic anomalies, or unusual concentrations of certain elements that could suggest industrial activity without leaving behind traditional archaeological evidence. For example, if a pre-human civilization had engaged in large-scale fossil fuel combustion, the carbon isotope ratio in sediments from their time might show a distinct deviation, similar to the Anthropocene signal we are creating today. Likewise, widespread production of synthetic compounds like plastics or fluorinated gases could leave chemical residues that persist long after physical artifacts are gone. Yet even these clues would be at risk of dispersal and dilution over vast stretches of geological time, making detection extremely difficult. This erosion of evidence is compounded by the uneven preservation of Earth's surface. The geological record is incomplete. Some eras are richly documented, while others are sparse or missing entirely due to erosion, non-deposition, or later geological activity. Entire continents' worth of rock from certain time periods have been lost to subduction or transformed into metamorphic rock, erasing fine details of their history. In many cases, the rocks we can study are marine sediments, which better preserve fossils of ocean life than the remains of land-based ecosystems or civilizations. If a prior civilization existed primarily on land, its traces might be disproportionately absent from the surviving geological record. All of this underscores why the Silurian Hypothesis does not claim direct evidence for a pre-human technological species. Instead, it emphasizes the difficulty of finding such evidence even if it did exist. In geological terms, the survival of clear, unambiguous artifacts over tens of millions of years is so unlikely that scientists would instead need to rely on subtler signals, patterns of chemical change, unusual isotope ratios, or other markers embedded in rocks and ice cores. These too would be rare and could be explained by natural processes, meaning extraordinary care would be needed to interpret them correctly. The fleeting nature of human civilization in Earth's deep time is humbling. It challenges the notion that the absence of evidence is evidence of absence, reminding us that our planet is a restless, ever-changing system in which the past is constantly being rewritten. Even the great pyramids, skyscrapers, and spaceports of today are temporary, destined to fade into dust or be swallowed by shifting landscapes if left to the forces of nature. If there were civilizations before us, beings who built, mined, manufactured, and explored, they may have left only whispers in the geological record, and we may be searching for traces that time has long since erased. This is not a failure of our technology or imagination, but rather a testament to the scale and power of Earth's geological clock, where even the grandest achievements are fleeting notes in an ancient, ongoing symphony. If an advanced civilization had existed long before humans, and its physical structures had long since vanished under the relentless march of geological time, the only remnants of its presence might be subtle, indirect traces locked away in the Earth's geological record. These would not be the obvious artifacts we are accustomed to finding from human history, buildings, tools, roads, but instead chemical and isotopic fingerprints that persist long after the physical world they belong to has crumbled. Understanding these traces requires looking at the way human industrial activity already leaves its own signature, and then asking whether something similar could survive for tens of millions of years. One of the most significant areas of focus is sediment analysis. Sediments, whether deposited in oceans, lakes, or floodplains, serve as long-term archives of environmental change. They form layer by layer, each stratum capturing chemical and physical details of the time it was laid down. Deep-sea sediments, in particular, can remain relatively undisturbed for millions of years. If a pre-human civilization had extracted and processed metals on a large scale, mined rare elements, or manufactured synthetic materials, these activities could have altered sediment chemistry in detectable ways. Even when corrosion and decay obliterate original objects, the materials they were made from can persist in altered forms, sometimes as distinctive mineral or elemental deposits. Metals are a prime example. Human industry produces vast quantities of refined metals, aluminum, copper, steel alloys, that differ in purity and distribution from naturally occurring deposits. In nature, aluminum is almost always bound in minerals like bauxite and is rarely found in a pure metallic form. Industrial processes, however, refine it into pure, corrosion-resistant metal used in transportation, construction, and packaging. Over millions of years, even pure aluminum will oxidize, but the chemical profile it leaves behind may be different from natural sources. Geologists looking for signs of a vanished civilization would search for layers of sediment or rock with anomalously high concentrations of certain metals in ratios inconsistent with natural ore formation. The same principle applies to rare earth elements, crucial for modern electronics, which are normally dispersed in very low concentrations, but might appear in unusual abundance if heavily mined and discarded into the environment. Artificial radioactive isotopes are another telling clue. Nuclear technology, whether in the form of power generation, medical isotopes, or weapons testing, produces isotopes that do not occur naturally in significant amounts, or that have half-lives long enough to be detectable millions of years later. For example, plutonium-244 has a half-life of about 80 million years, meaning that traces could remain measurable for an extraordinarily long time. If a pre-human civilization had mastered nuclear technology, even a small fraction of these isotopes could persist as a geological anomaly. Importantly, such isotopes would not appear evenly distributed across the globe. They would likely be concentrated near industrial centers or fallout zones. A paleogeochemist investigating ancient sediments might stumble upon such an anomaly without any immediate explanation, unless they entertained the possibility of a lost technological age. Changes in greenhouse gases present another avenue of detection. Human activity, especially the burning of fossil fuels, has driven a rapid rise in atmospheric CO2 and methane, along with changes in the ratio of carbon isotopes, specifically an increase in the lighter carbon-12 isotope relative to carbon-13. This isotopic shift, known as the Suez effect, is tied directly to the combustion of ancient organic matter. If a previous industrial civilization had similarly relied on fossil carbon, we might find a sharp, geologically brief spike in CO2 levels preserved in ice cores, marine carbonate deposits, or other climate proxies. Unlike tectonic or volcanic CO2 spikes, which can be linked to known geological events, an industrial signature might occur without any corresponding volcanic layer or asteroid impact. Methane provides its own distinct signature. While natural methane releases, such as from wetlands, clathrate destabilization, or volcanic eruptions, are well understood, an ancient surge in methane could also be tied to agriculture, livestock domestication, or industrial leakage. Detecting such a surge in the deep past would require correlating it with other industrial indicators to avoid mistaking it for a purely natural phenomenon. Synthetic chemicals like plastics offer perhaps the most striking potential signature of industrial activity, though their long-term survival is complex. Most plastics degrade relatively quickly in surface conditions, but some forms, especially microplastics, can persist in certain environments for far longer. In anaerobic conditions, such as in deep-sea sediments, plastic particles can be sealed away from oxygen and sunlight, slowing their breakdown to a crawl. Over millions of years, even if the original polymers are gone, they might leave behind unusual hydrocarbon residues or distinctive microfossils in the form of shaped particles that have no natural origin. These technofossils would be entirely alien to the biosphere of their time. Future scientists examining ancient seabeds might be puzzled by such uniform, highly processed particulates embedded in rock. Beyond plastics, industrial chemistry produces compounds that are extremely resistant to breakdown: polychlorinated biphenyls, PCBs, certain fluorinated chemicals like PFAS, forever chemicals, and heavy synthetic dyes. These compounds could adsorb to sediments and resist chemical alteration for vast timescales. Even if molecular structures eventually degrade, they could leave unique elemental or isotopic residues marking the layer in which they once resided. Detecting these signals would not be straightforward. Earth's geological record is patchy, with many sequences lost to erosion, metamorphism, or subduction into the mantle. Additionally, unusual chemical layers can have multiple explanations: volcanic activity, asteroid impacts, ocean anoxia events, or massive wildfires can all produce sharp geochemical changes. The challenge would be to differentiate a technological signature from these natural processes. That requires looking for clusters of anomalies that together suggest industrial activity. For example, a spike in heavy metal concentrations alone might be volcanic in origin, but if that spike coincided with unusual synthetic chemical residues, radioactive isotope anomalies, and a sudden CO2 increase without volcanic ash, the case for an artificial cause would strengthen. Deep sea cores offer one of the best preservation environments for these potential signatures. In the open ocean, sediments accumulate slowly but steadily, and disturbances are minimal compared to terrestrial environments. If an ancient civilization existed, it is possible that its chemical fingerprints are locked away beneath hundreds of meters of layered sediment, awaiting discovery by a drilling expedition. Similarly, certain lake beds and peat bogs can preserve fine chemical details for immense periods of time. Ice cores, though limited to the relatively recent past, hundreds of thousands to a few million years at most, could also trap atmospheric gas samples, providing a direct window into ancient air composition. In considering these possibilities, it is important to remember that the Silurian hypothesis is not asserting that such a civilization definitely existed. Instead, it frames the question as a test of our own detectability. If humans were to vanish tomorrow, what would remain of our presence in the far future? How would another intelligent species, tens of millions of years from now, even know we were here? The geological signatures we leave, our altered sediments, our synthetic chemicals, our isotope ratios, are the same kinds of clues we would need to look for in the deep past. The search for such traces would not only test the hypothesis, but also sharpen our understanding of Earth's own history. By learning to identify and separate industrial signals from natural events, scientists could more accurately reconstruct climate patterns, extinction events, and biogeochemical cycles. In this way, the study of hypothetical ancient civilizations becomes a tool for improving geology, climatology, and planetary science as a whole. Ultimately, detectable traces in the geological record represent the only realistic way we could ever confirm the existence of a pre-human technological age. Artifacts crumble, cities fall, and continents drift, but chemistry is stubborn. It leaves fingerprints even when the hands themselves are gone. If such a civilization ever walked the earth, its ghost may still be out there, not in ruins or relics, but in the quiet, enduring language of stone, sediment, and isotope. An industrial civilization does not merely rearrange stones and metals at the surface. It pushes on the great biogeochemical gears of a planet. Those gears, carbon, nitrogen, sulfur, phosphorus, trace metals, water, and calcium carbonate equilibria in the oceans, respond in measurable, often tightly coupled ways. If a technological species had risen and fallen long before humans, the most durable echo of its presence would not be tidy ruins, but a suite of climate and environmental fingerprints impressed into sediments, carbonates, and fossil chemistry. Reading those fingerprints is less about finding a single smoking gun and more about recognizing a coordinated pattern: abrupt greenhouse forcing, distinctive isotopic drifts, accelerated weathering and nutrient cycling, acidification signatures in the seas, reorganization of vegetation preserved by pollen spectra and charcoal, unusual trace metal distributions, and a biotic response that looks like a fast, selective extinction pulse. The Silurian Hypothesis uses our own Anthropocene as a calibration target, and then asks which of these markers could persist for millions of years, the combinations of which would be difficult to mimic with purely natural processes. The carbon cycle is the central stage on which industrial activity leaves its clearest signal. When a civilization burns fossil carbon at scale, it moves isotopically light carbon, rich in the 12C isotope relative to 13C, from geological storage into the fast atmosphere ocean biosphere reservoir. That pulse is recorded as a negative excursion in the carbon isotope ratio, typically measured as delta 13C in multiple archives: marine carbonates, organic rich shales, pedogenic carbonates in paleosols, and sometimes in the carbonate skeletons of marine microfossils. Industrial-era combustion also leaves a characteristic Suez effect, in which the delta to the power of 13C of atmospheric CO2 declines, while radiocarbon delta to the power of 14C is diluted by 14C-free fossil carbon. The radiocarbon aspect will not persist on multi-million-year horizons, because 14C decays quickly, but the stable carbon imprint can. In the far future, a geologist who extracts a deep-sea core spanning the interval of an industrial age would expect to see a geologically abrupt drop in delta to the power of 13C of bulk carbonate and organic matter, potentially a few per mil in magnitude if emissions are large and rapid. Alone, a carbon isotope excursion is not diagnostic. Natural events such as the Paleocene-Eocene thermal maximum, PETM, and Cretaceous ocean anoxic events, OAEs, also show pronounced negative delta to the power of 13C shifts. What strengthens an industrial interpretation is the pace, pattern, and bundle of coeval markers. Human-scale perturbations unfold over centuries to a few millennia, essentially instantaneous in stratigraphic terms, so an industrial delta 13C excursion would begin sharply, perhaps within a single bioturbated burrowed layer in slowly accumulating pelagic muds, and correlate globally across basins without the volcanic ash layers and mercury to thallium ratios expected of large igneous province volcanism. Greenhouse forcing from fossil carbon warms the climate, and that warmth itself imprints on the geological record. Oxygen isotopes, delta 18O, in the calcite of foraminifera and other marine fossils respond to both temperature and global ice volume. In a greenhouse spike with minimal change in ice sheets, planktonic foraminifera typically record a negative delta 18O shift, lighter values, consistent with warmer surface waters. Benthic foraminifera pick up deep ocean warming with a lag as heat penetrates the abyss. When ice sheets retreat, seawater delta 18O becomes lighter, compounding the temperature signal. The magnitude of the anthropogenic scale shift is small compared with the vast swings of glacial-interglacial cycles, but the tempo is distinctive, centuries to millennia, rather than the orbital pacing of tens to hundreds of thousands of years. In condensed sections or high-accumulation marine margins that preserve submillennial resolution, an industrial age warming should appear as a steep inflection in delta to the power of 18O and coccolithophore assemblages, paired with changes in foraminiferal magnesium to calcium ratios that track temperature independently of oxygen isotopes. Ocean acidification is the other hallmark of fossil fuel CO2. When CO2 dissolves into seawater, it forms carbonic acid, lowering pH and reducing carbonate ion concentration. That shift has several durable proxies. First, the percentage of cacao-3 in pelagic sediments falls as the carbonate compensation depth (CCD) shoals. Aragonitic and high Mg calcitic skeletons dissolve preferentially. In deep-sea sections that normally sit above the lidocaine, a transient interval of carbonate-poor red clay or a visible dissolution surface can mark a strong, rapid acidification pulse. Second, boron isotopes, delta-11b in foraminiferal calcite capture surface ocean pH. Lower pH depresses delta-11b. Third, elemental ratios such as B/Ca and UCA in foraminifera change with carbonate chemistry and saturation state, adding cross-checks. Reefs, being dominated by aragonite and high Mg calcite, leave an especially sensitive archive. An acidification interval curtails reef accretion, shifts coral community composition, and may be preserved as a reef gap or as rubble layers with elevated dissolution features. While natural CO2 injections from volcanism or methane clathrate destabilization can also acidify the ocean, the industrial pattern is abrupt onset, without the telltale volcanic ash beds, with coeval spikes in combustion-derived aerosols and pollutants, and with a pollen record on land showing rapid human-like vegetation reorganization. Combustion at industrial scale also changes the atmosphere's aerosol loading and the sulfur and nitrogen cycles. Coal and heavy oil contain sulfur. Their combustion releases SO2, which oxidizes to sulfate aerosols and deposits as acid rain. Lakes and peatlands faithfully record that deposition as layers with elevated sulfur content and shifts in sulfur isotopes, delta-34S, sometimes accompanied by changes in diatom assemblages and a decline in carbonate-preserved taxa due to acidification. In limestones and speleothems, acid rain can leave growth hiatuses and subtle geochemical excursions. On million-year timescales, the fine detail of lake verves is unlikely to persist everywhere, but the sulfur signal can be preserved by pyrite and gypsum in sediments and by altered weathering intensities of soils that later lithify. Nitrogen is even more diagnostic. The Haber-Bosch process fixes atmospheric N2 into ammonia to produce fertilizers at scales rivaling natural terrestrial fixation, altering the delta-15N of soils, riverine nitrate, and ultimately sedimentary organic nitrogen. Coastal and lacustrine sediments often show a shift in bulk delta-15 nitrogen and in compound-specific amino acid nitrogen isotopes associated with fertilizer use and manure inputs, accompanied by eutrophication, seasonal hypoxia, and the development of laminated anoxic muds. Over geologic time, such laminated intervals can become organic-rich shales with distinctive trace metal enrichments, molybdenum, uranium, vanadium, that form under low oxygen conditions. OAEs display similar features, but the anthropogenic-like version comes with parallel markers, spheroidal fly ash particles, unusual ratios of combustion-derived polycyclic aromatic hydrocarbons, PAHs, and an abrupt arrival of invasive terrestrial pollen taxa that do not match climate-driven biome shifts. The hydrological and geomorphological consequences of agriculture and urbanization also scale up to geological signals. Widespread soil tillage and deforestation accelerate erosion, increasing terrigenous sediment flux to rivers, at least until dams intervene. The result is a two-step fingerprint, an initial century-scale pulse of coarse classics and silts reaching floodplains and continental margins, followed by a reduction in sediment delivery as thousands of dams impound sediments upstream. Stratigraphically, deltas may show an early 20th century progradation front that abruptly stalls or retreats despite continued sea level rise, creating revinement surfaces and transgressive estuarine fills out of cadence with natural sediment supply histories. Offshore, grain-size spectra in shelf cores show a fining upward trend linked to sediment starvation, while geochemical markers indicate rising organic matter preservation from eutrophication. These patterns can be lithified into distinct packages: angular unconformities, estuarine mudstones with laminated fabrics, and condensed carbonate horizons that, when placed alongside the chemical fingerprints, sketch the geomorphic footprint of a brief but intense industrial phase. Ocean ecosystems respond rapidly to warming, acidification, and nutrient pollution, and those responses fossilize. Plankton communities reorganize, often favoring smaller, thermophilic, opportunistic species over larger, cold-water specialists. In the rock record, this shows up as turnovers in foraminiferal and coccolithophore assemblages, dwarfing trends in shell size, and temporary disappearances, pseudo-extinctions, of sensitive taxa. Benthic foraminifera in oxygen-poor zones decline or switch to low oxygen-tolerant species. Laminated organic-rich layers accumulate where bioturbation ceases. Reef crises present as carbonate factory shutdowns, with frameworks replaced by rubble, mirabilities, or non-reef carbonates. These crises often track acidification intervals indicated by boron isotopes. If industrial forcing were strong enough, deep-sea carbonate dissolution horizons would shoal, leaving a basin-wide marker bed of carbonate-poor clay, much like the clay caps of known hypothermal, but accompanied by those distinctive technogenic tracers. One should also expect a short, sharp perturbation to the methane budget. Methane's atmospheric lifetime is short, but sustained releases from fossil extraction and agriculture elevate CH4 and leave a carbon isotope imprint in methane-derived carbonates and potentially in clumped isotope compositions of carbonate cements formed in methane seep contexts. Rice agriculture and ruminant livestock are powerful biogenic sources. In wetland peats and lake sediments, methanogen biomarkers and associated isotopic shifts in sedimentary organic matter can record a sustained change in methanogenesis and methanotroph. In marine settings, enhanced methane oxidation associated with seepage can precipitate orthogenic carbonates with very low delta, 13C. If a pulse of industrial leakage triggered regional seep intensification, it might pepper shelf stratigraphy with unusually 13 C-depleted carbonate nodules temporally aligned with other Anthropocene-like markers. Beyond chemistry, the physical sedimentary fabric bears industrial fingerprints. Urbanization hardens watersheds, altering hydrographs and flood recurrence. Rivers incise and degrade in patterns out of equilibrium with climate alone. In the stratigraphy of alluvial plains, this translates into stacked channel belt sand bodies with unusual lateral continuity and engineered straightness at human scales, features easily erased by later reworking. But in rapidly subsiding basins, some engineered alignments might survive as subtle anisotropies in paleochannel architectures. Coastal structures, seawalls and artificial reefs are unlikely to persist as coherent artifacts on million-year horizons, but their influence on sediment baffling and localized scour could leave highly localized anomalies in grain-size distributions, again useful only when found alongside the global geochemical symphony. Time, of course, is the great eraser. Ice cores sublime, soils are reworked, lakes infill, and many shallow marine sections are later truncated. Yet the deep sea hoards secrets: pelagic clays, hemipelagic muds at continental margins, and rapidly buried estuarine fills are the planet's black boxes. Even after diagenesis, stable isotope records, trace metal enrichments, and microscopic technofossils can survive. The longer the interval since the event, the more we must rely on features that are not easily diffusively smoothed, step changes rather than gentle slopes, presence-absence of morphologically distinctive particles, and interlocking isotope systems that cannot all be nudged by a single natural mechanism in the same way at the same time. A civilization's climate footprint is therefore best sought not as a lone anomaly, but as a chorus. Carbon saying warming and fossil carbon, boron saying acidification, oxygen and MEMK saying temperature, nitrogen and redox metals saying eutrophication and hypoxia, trace metals and PAH saying combustion, pollen and charcoal saying agriculture and land clearing, and the fossil record whispering rapid, patterned loss. Modern human activity offers a unique real-time case study for understanding what an ancient industrial civilization's impact might look like if it had once existed on Earth. The comparison is valuable because the geological and environmental alterations we are making today provide a direct analogy for the kinds of traces a technologically capable species could leave behind, traces that might persist for millions of years. This is the essence of the Silurian hypothesis in practical terms. By studying ourselves, we create a framework for detecting others who may have come before. One of the clearest indicators of our presence is the emergence of a new human-made geological layer, what scientists increasingly refer to as the Anthropocene. This proposed epoch is defined by the unmistakable planetary-scale impacts humans have had on the Earth's systems. It's not just a matter of cultural or technological artifacts, but rather the lasting transformation of the planet's sedimentary, chemical, and biological makeup. Future geologists, even millions of years from now, would likely recognize this layer as distinct from all others that came before it. The Anthropocene is filled with materials and markers that simply do not appear in the natural geological record prior to our industrial age. One of the most unusual and enduring markers is the proliferation of plastic particles. Plastics, created from fossil fuels, are chemically stable enough to survive for extremely long periods under certain conditions. Over time, they break down into microplastics and nanoplastics, which can embed themselves deep in soils, sediments, and even ice layers. In some coastal environments, they combine with sand and other debris when heated, forming rock-like substances called plastglomerates. Unlike natural minerals, these hybrid formations are entirely synthetic in origin, and their chemical structure is unlike anything Earth produced prior to the rise of industrialized humans. In the deep future, long after cities and machines are gone, plastglomerates could remain as silent witnesses of our existence. Another defining signature is fly ash, a fine particulate byproduct of coal and other fossil fuel combustion. Fly ash particles are spherical, highly resistant to weathering, and chemically distinct. They are often transported long distances by atmospheric currents, ending up in soils, riverbeds, and ocean sediments far from their point of origin. Even if industrial infrastructure vanished, these tiny spherical remnants would remain detectable in the geological record. Over the course of millions of years, layers rich in fly ash could act as clear evidence of a period of intense fossil fuel burning, potentially pointing to an industrial civilization's energy dependence. Then there are radionuclides, radioactive isotopes produced by nuclear activity. Above-ground nuclear weapons testing in the mid-20th century injected isotopes such as plutonium-239, cesium-137, and carbon-14 anomalies into the environment. Some of these isotopes have half-lives stretching into tens of thousands or even millions of years, meaning they could persist far into the geological future. Importantly, many of these isotopes do not occur naturally in the concentrations created by human activity, making them highly distinctive. If intelligent beings were to examine sediment cores millions of years from now, they could identify this as a moment when nuclear technology was active on Earth, whether from peaceful applications, accidents, or weapons. The persistence of these materials is critical. Cities may erode, machines will corrode, and organic matter will decompose. But plastics, certain metals, and long-lived isotopes are stubborn. In the geological record, they could endure through multiple ice ages and tectonic shifts, buried in layers of rock and sediment. The very durability that makes them problematic for modern ecosystems also makes them excellent markers for identifying a civilization's presence across deep time. This comparison to our own impact raises an intriguing point. If a previous civilization existed on Earth millions of years ago, it may have left behind similar markers, perhaps subtle, degraded, or altered by geological processes, but still faintly present. For example, there might be unusual chemical deposits in ancient sediment layers, unexplained shifts in isotope ratios, or odd mineral combinations that don't match natural formation processes. These might currently be attributed to natural events, simply because we are not yet considering the possibility of an earlier industrial species. Our own geological fingerprints, plastics, fly ash, radionuclides, remind us that technology leaves patterns, and that those patterns may be detectable long after direct evidence is gone. The Anthropocene also teaches us something else: the scale and speed of change. In only a century and a half, industrial civilization has transformed the biosphere, altered atmospheric chemistry, reshaped coastlines, and driven unprecedented biodiversity loss. These rapid changes are not typical in Earth's natural cycles, except in the aftermath of catastrophic events like asteroid impacts or supervolcanic eruptions. If another species in the distant future were to study Earth, they might see our geological layer as a boundary event, a sudden and sharp shift marking the transition from one planetary state to another. This is the same kind of pattern geologists use to identify mass extinctions and other global transitions in the deep past. From a Silurian hypothesis perspective, this means that if a previous technological civilization existed, its own rapid transformation of the planet might be visible in much the same way. Even if the actual artifacts, buildings, vehicles, tools were erased by millions of years of erosion and plate tectonics, the environmental shock it caused could still be discernible. The trick is in recognizing which anomalies are natural and which might be artificial in origin. One of the more subtle implications is that our current understanding of the geological past might already contain such anomalies. For instance, there are periods in the fossil record where extinction rates spiked and certain chemical shifts occurred without an obvious explanation. In some cases, these are attributed to massive volcanic events, climate fluctuations, or changes in ocean chemistry. But could some of these unexplained patterns be the remnants of a civilization predating humanity? Without looking for industrial signatures, synthetic chemicals, metallurgical residues, or isotopic patterns distinct from known natural events, we might never know. This comparison also forces us to acknowledge the fragility of direct evidence. Our modern skyscrapers, roads, and digital infrastructure feel permanent to us, but they are fleeting in geological terms. In just a few thousand years without maintenance, most human structures would crumble and disappear beneath vegetation and sediment. In a million years, almost all visible signs would be gone. The only reason we might still be detectable is because of the unusual materials and chemical imprints we have left in the environment, markers far more persistent than stone or steel. In the long run, the Anthropocene will be a narrow but distinct slice of Earth's geological history. It will contain unmistakable signs of human existence, but it will also serve as a template for understanding what to look for if we ever seriously investigate the possibility of ancient pre-human civilizations. By studying our own impact now, we are effectively creating a guidebook for detecting others. This is perhaps the most profound aspect of the comparison. We are both the subject and the experiment. Our industrial footprint is not only shaping the planet's future, but also providing the exact kind of data that future scientists or alien archaeologists would use to determine if we ever existed. That same framework, applied in reverse, could help us identify civilizations from Earth's distant past, if any ever existed. The lesson is clear. Civilizations leave scars on their planets, and those scars, however faint, may be read if we know how to look. Technological and biological limits form one of the most critical aspects of the Silurian hypothesis, because they define not only the possible lifespan of a civilization, but also the likelihood of its evidence enduring for millions of years. No matter how advanced or widespread an industrial society becomes, it remains bound by the same planetary limitations that all living systems face: finite resources, environmental vulnerabilities, and the unpredictability of evolution. When we examine our own civilization, we can already see how delicate the balance truly is. Technological infrastructure is entirely dependent on a consistent supply of energy, raw materials, and stable environmental conditions. If any of these pillars were removed or significantly disrupted, the system would rapidly destabilize, leading to a collapse in societal complexity. Resource depletion is a particularly important factor. Any civilization reliant on industrial production inevitably consumes non-renewable resources at a pace faster than they can naturally replenish. Metals, fossil fuels, and certain rare minerals are all finite, and as they become harder to extract, the economic and logistical costs of maintaining technology escalate. Without alternative systems in place, this can lead to a cascading collapse where technological capacity is lost long before the knowledge to rebuild it is forgotten. Climate instability poses another major threat. Civilizations alter their own planetary systems, intentionally or unintentionally, through agriculture, deforestation, industrial emissions, and energy production. As atmospheric and oceanic conditions shift, ecosystems begin to falter. Crops fail, weather patterns grow erratic, and essential water supplies become unreliable. In human history, even minor climatic changes have led to famine, migration, and political unrest, and these shifts were often regional. For a truly global civilization, a large-scale climate event could have irreversible consequences. Ecological collapse often works in tandem with these factors. The destruction of biodiversity reduces ecosystem resilience, making it harder for nature to buffer against disruptions. Overexploitation of fisheries, overhunting, and the loss of pollinators or keystone species can destabilize entire food webs. Once ecological systems pass certain tipping points, recovery can take centuries or millennia, timescales far beyond what a struggling civilization might endure. When a civilization collapses, the biological aftermath becomes an evolutionary question. If any intelligent species once thrived millions of years before us, the odds of their direct descendants still existing today are incredibly slim. Extinction events, whether triggered by natural disasters, climate change, or self-inflicted environmental damage, tend to wipe out the largest and most specialized species first. Survivors are often smaller, more generalized organisms capable of adapting to rapidly changing conditions. Over millions of years, these survivors would evolve into entirely new forms, possibly erasing any outward resemblance to their intelligent ancestors. This makes it nearly impossible to identify a continuous lineage from a past technological civilization to present-day life forms. Fossil evidence of intelligent life would be rare for several reasons. Soft tissues such as skin, brain matter, and organs decompose rapidly, leaving behind only skeletal remains, and those bones themselves are vulnerable to erosion, scavenging, and chemical dissolution. For a skeleton to fossilize, it must be quickly buried in sediment under very specific conditions, such as within a river delta, lake bed, or shallow sea. Even then, the odds of that fossil surviving intact for millions of years and later being discovered are extraordinarily small. Most fossils we find are of abundant species that lived in environments conducive to preservation, not rare intelligent creatures with specialized habitats. Industrial ruins degrade far faster than biological fossils under natural conditions. Concrete and steel may seem durable, but in geological timeframes, they are ephemeral. Concrete slowly crumbles through chemical weathering, steel oxidizes into rust, and glass fractures into sand-like particles. Even our most monumental architecture, skyscrapers, dams, and bridges, would be unrecognizable rubble within tens of thousands of years. In a million years, almost nothing of human cities would remain on the surface. Underground infrastructure, such as subway tunnels, might survive longer, but tectonic activity, groundwater erosion, and sedimentation would eventually distort or destroy them as well. Preservation of knowledge and artifacts is therefore highly dependent on rare, stable environments. Deep caves, shielded from weather, earthquakes, and most biological activity, could potentially protect artifacts for much longer than surface exposure allows. Ocean sediments, where low oxygen levels reduce decay and scavenger activity, could entomb technological debris in layers of mud, preserving them as subtle anomalies in mineral composition. Similarly, ice sheets, if they remain stable, could lock away physical objects or atmospheric traces for hundreds of thousands of years. However, ice is far from permanent in the deep geological record. Over millions of years it melts, refreezes and flows, eventually erasing or scattering its contents. One of the most intriguing implications of these limits is that an ancient industrial civilization could have flourished for thousands, even hundreds of thousands of years, and still be almost invisible to us today. Given the planet's capacity for transformation, driven by plate tectonics, erosion and climate cycles, the survival of even small-scale artifacts over deep time is a statistical rarity. Without specific and deliberate preservation methods, their existence could be erased long before another intelligent species emerged to search for them. If we consider the brief window of time in which humans have existed, and the even shorter period in which we have been technologically capable, it becomes clear that the traces of such a civilization are both fragile and fleeting. This perspective also forces us to think critically about our own future. If we were to collapse tomorrow, what would we actually leave behind for the distant future to find? Perhaps a thin layer in the geological record containing microscopic plastic particles, unusual isotopic ratios from our carbon emissions, and a faint trace of artificial radionuclides from nuclear activity. These would be subtle, scattered clues, nothing like the towering monuments or sprawling cities that define our present. From the viewpoint of a future geologist or paleontologist, these clues could just as easily be dismissed as anomalies caused by natural processes, unless they were interpreted within the framework of a theory like the Silurian Hypothesis. In this way, the technological and biological limits faced by any civilization serve as both a cautionary tale and a scientific challenge. They remind us that planetary history is vast, our time upon it is short, and without deliberate preservation or extraordinary luck, our own existence could fade into obscurity just as easily as any hypothetical predecessor. The Silurian hypothesis pushes us to consider that the absence of evidence is not necessarily evidence of absence. It may simply be a reflection of the harsh reality of time, geology, and biology working against the preservation of civilization itself. The study of Earth's deep history in the context of the Silurian hypothesis has important implications for the search for extraterrestrial civilizations. By investigating whether there could have been a technological civilization before humans, scientists are forced to confront the possibility that technological life may not be a one-time occurrence on a planet. This means that a planet like Earth could have experienced multiple cycles of civilization and collapse over hundreds of millions of years. In the case of Earth, our geological record is a powerful archive of past events, but it is also one that is incomplete, eroded, and constantly rewritten by natural processes. Understanding how traces of our own industrial activity would appear millions of years from now allows us to better recognize what similar traces might look like on other worlds. The principle here is straightforward. If advanced civilizations existed in the past, either on Earth or elsewhere, their presence might be detectable not through direct observation of buildings or machines, but through persistent techno-signatures left in the planet's atmosphere, crust, or oceans. These could include unusual chemical residues, artificial isotopes, or climate disruptions, unlike those produced by natural cycles. On Earth, for example, our burning of fossil fuels has already altered the carbon isotope ratios in the atmosphere, a signal that could last for millions of years. In the same way, scientists could examine the atmospheres of exoplanets, planets orbiting other stars, for unusual gas compositions or temperature profiles that hint at technological activity. The search for extraterrestrial life has traditionally focused on detecting biosignatures, such as oxygen or methane in an atmosphere, which could indicate living organisms. But the Silurian hypothesis encourages researchers to think more broadly and include potential technosignatures as well. This is where studies of our own Anthropocene, the geological era marked by human activity, become critical. The plastics embedded in sediments, the synthetic compounds in soils, The artificial radionuclides from nuclear activity and the altered climate patterns are all features that could be detected remotely if they occurred on another planet. They may even be more detectable in some cases than signs of biology, since they can create highly unusual chemical combinations that nature rarely produces on its own. When applying this thinking to the search for extraterrestrial civilizations, one must also consider the challenge of timing. Civilizations, as far as we know, may be inherently short-lived on cosmic timescales. If a technological society only lasts a few thousand years before collapsing due to environmental, resource, or social crises, then the odds of two civilizations existing at the same time and being able to detect each other are extremely low. This concept is part of what scientists call the temporal aspect of the Fermi paradox, the question of why we haven't detected extraterrestrial life, despite the high probability that it exists somewhere in the universe. Furthermore, even if a civilization leaves detectable traces, those traces might not persist indefinitely. Geological processes, atmospheric changes, and cosmic events such as asteroid impacts or stellar activity can gradually erase or disguise the evidence. That means that the window for detection could be far smaller than we imagine. For example, a planet that hosted a civilization 1 billion years ago might today show no obvious signs of that civilization's existence unless the evidence was preserved in an extraordinarily stable environment. This realization adds urgency to the search for technosignatures, since it implies that catching them in the act, or soon after, could be the only way to confirm their existence. There is also a philosophical aspect to these implications. If Earth has had multiple cycles of civilization and collapse, and if other planets may have experienced the same, it suggests that the development of technological intelligence is not necessarily the end goal of evolution, but just one stage in a repeating planetary process. In that case, finding another civilization in the universe might mean finding one in the middle of its own environmental crisis, or just before its collapse, mirroring our own precarious situation today. This possibility can help reframe our approach to the search for extraterrestrial intelligence, SETI, by reminding us that what we're really looking for is not just life, but life at a specific and fleeting technological stage. This also influences the way space missions are designed. Telescopes and probes might be configured not only to detect habitability and biosignatures, but also to identify industrial pollutants, greenhouse gas imbalances, or waste products in alien atmospheres. The James Webb Space Telescope and its successors could play a role here by performing detailed spectroscopic analyses of exoplanet atmospheres, searching for combinations of gases that are unlikely to arise naturally. For example, the simultaneous presence of methane and carbon dioxide in certain ratios might suggest industrial activity, since methane breaks down quickly in most atmospheres and would need a continuous source to remain detectable. The Silurian Hypothesis does more than raise an intriguing scientific possibility. It offers a profound mirror in which humanity can study itself. By contemplating whether a past industrial civilization might have existed long before us, we are forced to confront a sobering question. If such a civilization once thrived and fell, could the same fate await us? And if it did happen before, what clues, if any, did they leave behind, and how quickly did the Earth erase them? This perspective shifts the discussion from mere curiosity to one of urgent relevance. Our civilization, advanced and powerful as it seems today, is still subject to the same planetary and ecological constraints that have shaped all life throughout Earth's history. If the geological record holds even the faintest traces of previous industrial societies, it would suggest that technological civilizations are not immune to the cycles of rise and collapse that govern the deep past. In considering this, the hypothesis urges us to study the geological record not simply as a static archive, but as a dynamic record of planetary resilience and vulnerability. The Earth has undergone numerous mass extinction events, climate upheavals, and radical transformations in atmospheric composition. Many of these changes happened over spans of time much shorter than the age of the planet, and some were triggered or exacerbated by biological or environmental feedback loops. If ancient industrial activity had played a role in any of them, it could mean that our own industrial footprint, so obvious to us today, might someday be reduced to subtle chemical or isotopic anomalies that could be overlooked without careful, targeted study. This leads to a central warning embedded in the Silurian hypothesis, that the apparent permanence of our own civilization's influence is an illusion. We build vast cities, alter landscapes, and release unprecedented amounts of greenhouse gases and synthetic compounds into the environment. But in geological terms, these might fade into obscurity far faster than we expect. Sediment deposition, erosion, tectonic activity, and chemical weathering can erase visible traces in relatively short periods when measured against the scale of millions of years. Only certain types of markers, such as shifts in stable isotope ratios, the presence of synthetic molecules unlikely to occur naturally, or rare metal concentrations, stand a chance of surviving into the far future. From this perspective, our current environmental impact becomes both a subject of study and a potential message to whoever might inherit the Earth after us. The hypothesis essentially asks us, if we were to vanish tomorrow, what would survive of our presence? Would our legacy be an unmistakable signal to a future intelligence, or would it be so subtle that they too would debate whether we had ever existed at all? This thought exercise highlights the fragility of human achievement when measured against the deep time forces of geology. It also compels us to consider how deliberate we want to be about leaving a detectable record, not only as a matter of pride, but as a safeguard for the continuity of knowledge. The survival imperative becomes clearer when we look at the historical resilience, or lack thereof, of complex societies. Many human civilizations have collapsed due to a combination of environmental degradation, overexploitation of resources, climate change, and political instability. While these collapses occurred on a much shorter timescale than the one considered in the Silurian hypothesis, they still demonstrate a recurring pattern, that complexity does not guarantee survival. Indeed, the more complex and interdependent a system becomes, the more vulnerable it can be to cascading failures. Our current global civilization is arguably the most interconnected in history, meaning that local disruptions can quickly escalate into global crises. This makes the lessons of the Silurian hypothesis not only intellectually stimulating but also urgently practical. One of its key contributions is to encourage a more nuanced reading of the geological record. For example, scientists examining deep-sea sediment cores might find layers with unusual isotopic compositions, abrupt changes in microfossil populations, or traces of synthetic materials. Under conventional interpretation, these anomalies might be attributed to volcanic events, asteroid impacts, or natural climate oscillations. But if we keep the possibility of past industrial activity in mind, we might apply more stringent criteria to test alternative explanations. This doesn't mean jumping to conclusions about ancient civilizations, but rather remaining open to the possibility that some patterns in the record could have non-natural origins. This approach can also be applied in reverse to our own time. We can study the distinct markers we are leaving, the so-called Anthropocene signature, and project how they might degrade over time. Such projections can inform both our understanding of the persistence of industrial activity in the geological record and our strategies for environmental management. For example, the persistence of certain plastics and synthetic compounds might mean they are among the most enduring signals of our presence. Conversely, the rapid breakdown of other materials might show us how easily our works could vanish without a trace. Beyond the realm of earth science, the Silurian hypothesis resonates strongly with astrobiology. If advanced civilizations tend to be rare, short-lived, and geologically elusive, then our chances of detecting them on other planets may be much lower than we would hope. This is particularly relevant to the search for technosignatures, indicators of technology-based activity, in the atmospheres or surfaces of exoplanets. We might not find bustling cities or orbiting satellites. Instead, we may need to look for subtle shifts in chemical composition, unusual isotopic ratios, or anomalous heat signatures that could point to past industrial activity. Understanding our own potential disappearance could therefore sharpen our ability to recognize the faded fingerprints of others. From a philosophical standpoint, the hypothesis invites a kind of planetary self-reflection. It pushes us to see ourselves not as the inevitable pinnacle of evolution, but as a temporary phase in the long history of life. This shift in perspective can be both humbling and motivating. On the one hand, it reminds us that survival is not guaranteed and that even the most advanced civilizations may eventually be erased. On the other, it challenges us to take conscious steps to extend our longevity, both by mitigating existential risks and by preserving knowledge in ways that can survive deep time. This could mean developing archives stored in stable geological formations, creating redundant repositories across the planet, or even placing information in space where it might remain intact for millions of years. The hypothesis also underscores the importance of resilience over mere technological advancement. A society can have incredible technological prowess, yet still be undone by environmental collapse, resource exhaustion, or self-inflicted catastrophes. The message here is clear. Technological progress without sustainable stewardship of the planet is a fragile foundation for long-term survival. By studying past planetary changes, whether or not they were influenced by prior intelligent life, we can gain insight into the thresholds and tipping points we must avoid. Ultimately, the Silurian hypothesis frames the search for past civilizations not as idle speculation, but as an exercise in understanding the lifespan of technological societies. It shows that our existence is bound by the same planetary limits as any hypothetical predecessors. The geological and climatic shifts we set in motion today will shape the world far beyond our own lifetimes, potentially determining whether future beings find a clear signal of our existence or just a faint and ambiguous trace. By taking this lesson seriously, we can begin to make choices that increase the odds that our story endures, not as a cautionary tale of collapse, but as a sustained chapter in the history of life on Earth. In this way, the hypothesis becomes both a scientific tool and a moral compass. It demands that we look beyond the short-term horizons of politics and economics to consider the long arc of planetary history. The very act of asking whether another civilization might have come and gone before us forces us to imagine our own absence, and more importantly, what we can do to prevent it. This is why the Silurian hypothesis, despite its speculative nature, holds such profound relevance. It is not only about the past, but also about safeguarding the future. The Silurian hypothesis has sparked not just curiosity, but also rigorous debate within the scientific community. At its core, the idea is intriguing. The possibility that another advanced civilization may have risen and fallen on Earth long before humanity. Yet, despite its compelling nature, the hypothesis is met with skepticism, largely because no direct, unambiguous artifacts of such a civilization have ever been found. This lack of physical evidence is the most significant obstacle to its acceptance as anything more than an intellectual exercise. The Earth's surface is constantly reshaped by natural forces such as plate tectonics, erosion, and sedimentation. And while these processes could feasibly erase most signs of an ancient industrial society, critics still find it difficult to accept that absolutely no unmistakable traces remain after millions of years. Geological anomalies, which might at first glance seem like evidence of advanced activity, are often explained by natural processes. For example, sudden spikes in atmospheric carbon dioxide or unusual metal deposits could be the result of massive volcanic events, asteroid impacts, or unique mineral formations rather than industrial emissions. The burden of proof lies heavily on proponents of the Silurian hypothesis to differentiate between these naturally occurring phenomena and those potentially created by intelligent beings. Without conclusive markers, such as synthetic compounds with no known natural origin or isotopic ratios impossible to produce without advanced technology, skeptics argue that speculation cannot move into the realm of established science. One of the most persistent challenges lies in identifying what counts as a long-term marker of civilization. Critics point out that modern human activity is leaving a distinct geological fingerprint, but even then, it's uncertain how much of this record will survive millions of years. Plastics, industrial byproducts, and radioactive isotopes might remain detectable for long spans, but over tens of millions of years, the vast majority could be destroyed or buried beyond reach. If our own era's defining traces may eventually become faint, the odds of detecting a previous civilization's remnants are even lower, especially if it existed during an era of vastly different climate and geography. Proponents of the Silurian hypothesis, despite acknowledging the lack of direct evidence for a pre-human industrial civilization, believe that this absence should not be interpreted as conclusive proof against the idea. In their view, the absence of evidence is not the same as evidence of absence, and human history is filled with examples where scientific understanding has been dramatically reshaped by discoveries that were once considered implausible or outright impossible. They point out that science has repeatedly encountered transformative findings that have forced a re-evaluation of long-held beliefs. For example, before the late 20th century, the idea that life could survive in extreme conditions, such as boiling hydrothermal vents at the bottom of the ocean, miles beneath the Earth's crust, or in the frozen, radiation-bathed wastes of Antarctica, was not widely accepted. Yet the discovery of extremophiles microorganisms capable of thriving in such seemingly uninhabitable environments completely altered the scientific understanding of life's boundaries. These discoveries also expanded the search for life beyond Earth, proving that it can exist in conditions far different from those on the surface of our planet. Supporters of the hypothesis draw a direct parallel between these shifts in perspective and the potential search for evidence of a pre-human civilization. They argue that just because we have not yet uncovered definitive traces does not mean such traces do not exist. It might simply mean we have been looking in the wrong places or with the wrong tools. Archaeology and paleontology themselves are fields built upon fragmentary evidence, where monumental conclusions can arise from surprisingly small findings. For instance, the identification of previously unknown hominin species, such as Homo floresiensis or Denisovans, often came from only a handful of bone fragments, teeth, or genetic material. Before these discoveries, the existence of such species was not only unknown but would have seemed unlikely given the available evidence. The lesson here, proponents argue, is that enormous gaps can exist in the fossil and archaeological records, and those gaps can conceal entire chapters of history. Applying this principle to the Silurian hypothesis, the reasoning is straightforward. If we have managed to miss entire species of hominins from the relatively recent past, it is plausible that evidence of an industrial civilization from millions of years ago could have eluded us entirely. Geological processes naturally erase and recycle much of the planet's surface over deep time. Tectonic activity can bury entire regions, subduction zones can drag crustal material deep into the mantle, erosion can strip away layers, and sedimentation can bury evidence under kilometers of rock. Over tens of millions of years, even durable artifacts could be destroyed, metamorphosed, or dispersed into unrecognizable forms. The industrial footprint of modern humanity, our buildings, roads, cities, and even waste, might be almost entirely erased in that timescale, leaving behind only subtle chemical or isotopic traces. Proponents also highlight the limitations of current sampling and analysis. Much of Earth's deep past remains unexplored at a fine-grained level. Geological sampling tends to focus on particular regions for reasons of accessibility, resource exploration, or academic interest, which means vast areas of the planet's crust have not been systematically examined for unusual patterns that might hint at industrial activity. Even when anomalies in climate records or chemical compositions are found, they are often attributed to natural causes without further exploration for artificial explanations. For instance, a spike in carbon isotopes might be assumed to reflect volcanic activity or methane release from clathrates, but proponents suggest that such anomalies could also, in theory, result from industrial emissions, whether from our civilization or from one that predated it. Without targeted testing for synthetic compounds or isotopic signatures that cannot be explained by known natural processes, these possibilities remain unexplored. The argument is further strengthened by pointing out that the tools and methods for detecting such faint traces have only recently begun to reach the necessary levels of sensitivity. Techniques in geochemistry, for example, now allow scientists to detect trace amounts of isotopes and compounds in concentrations as low as parts per trillion. Similarly, advanced imaging and scanning technologies can reveal microstructures or inclusions within rock samples that would have been invisible even a few decades ago. In the same way that improved genetic analysis techniques suddenly revealed the existence of Denisovans from a single finger bone, improved geochemical and mineralogical techniques could one day reveal evidence of an ancient industrial process from a small, overlooked sample. Supporters of the hypothesis emphasize the importance of focusing research on very specific geological timeframes and locations. They believe that the best opportunities to uncover such evidence lie in strata that already show unexplained anomalies in climate or chemical composition. For example, certain rapid warming or cooling events in the geological record remain only partially explained, and some mass extinction events still have debated causes. Proponents argue that while natural explanations are the default, these intervals should be examined with an open mind for potential artificial contributions. If a spike in global temperature occurred alongside a mysterious deposit of synthetic-looking material, it would demand a deeper investigation. Even if the artificial explanation ultimately proves incorrect, the process of searching could reveal new information about Earth's natural history. Another dimension to their reasoning is that the search for ancient industrial signatures would not only test the Silurian hypothesis, but also have practical benefits for modern science. In developing the tools and methodologies to detect extremely subtle signs of past civilizations, researchers would also be enhancing the techniques used in the search for extraterrestrial life. The same kind of isotopic and chemical analyses that could detect an ancient industrial event on Earth could also be applied to Martian rocks, lunar samples, or material from asteroids. In this way, the search has a dual purpose. It addresses a fascinating possibility about our own planet's history, while simultaneously preparing us for more advanced planetary exploration. Proponents also note the psychological and philosophical value of keeping the question open. They believe that prematurely dismissing the possibility of a pre-human civilization limits scientific curiosity and closes off potentially valuable lines of inquiry. Science advances most effectively when it is willing to test unlikely hypotheses, so long as those hypotheses are examined rigorously. Just as the concept of continental drift was once dismissed as fringe before plate tectonics provided overwhelming evidence, or as the idea of meteorite impacts shaping Earth's history was initially resisted before the Chicxulub crater was linked to the extinction of the dinosaurs, so too might the idea of a deep-time industrial civilization seem far-fetched now, but prove more reasonable in light of future discoveries. The Silurian hypothesis, as its supporters see it, does not require a leap into conspiracy or pseudoscience. It is a question framed in terms of measurable, testable evidence. It asks, if an industrial civilization existed tens or hundreds of millions of years ago, what would be left, and could we recognize it? The only way to answer that question is through targeted, well-designed research. That means selecting promising sites, drilling deep into undisturbed sediments, applying the most sensitive chemical and isotopic analyses, and comparing results against the full range of known natural processes. Such research requires collaboration between multiple scientific disciplines: geology, chemistry, paleoclimatology, archaeology, and even astrophysics, because the clues, if they exist, are likely to be subtle and ambiguous. The history of science offers ample cautionary tales about dismissing possibilities too soon. The discovery of life in boiling hydrothermal vents rewrote the rules of biology, and expanded the search for life beyond Earth. The recognition of multiple ancient human relatives redefined our understanding of human evolution. The acceptance of catastrophic asteroid impacts transformed the field of geology. In each case, the breakthrough was not just about new data, but about the willingness to reinterpret old data in light of new ideas. Proponents of the Silurian hypothesis believed that the same openness could eventually lead to a paradigm shift in how we view the deep history of life and intelligence on Earth. They acknowledged that the odds may be low, but they also argue that the stakes are high. If such a civilization once existed, its fate could carry vital lessons for our own. Industrial activity leaves distinct and potentially dangerous signatures in the climate and biosphere, and if a previous civilization collapsed under the weight of its own environmental impact, understanding that process could help humanity avoid the same outcome. Even if the search yields no evidence, it would still contribute to our knowledge of how planetary systems preserve or erase the marks of civilization over geological time. The work could help calibrate the expectations of SETI researchers, refine models of planetary habitability, and sharpen our sense of how long industrial civilizations might last before vanishing without a trace. Importantly, the hypothesis serves a function beyond proving or disproving the existence of ancient civilizations. It compels scientists to think more deeply about how civilizations alter their planets, how those alterations are recorded in deep time, and how resilient such changes are in the face of geological processes. In this sense, the Silurian hypothesis acts as a scientific thought experiment, one that can help refine the methods used not only to study Earth's past, but also to search for extraterrestrial civilizations. If we fail to detect a possible industrial society on our own planet's deep timeline, it raises the possibility that we could also overlook similar evidence on other worlds. Even among skeptics, there is acknowledgement that the hypothesis encourages valuable interdisciplinary work, bringing together geologists, climatologists, archaeologists, and astrobiologists. The central challenge remains the same: to distinguish with high confidence between signatures left by natural processes and those that could only be created by intelligent life. Until such evidence is found and verified, the Silurian hypothesis will remain an open question, provocative, imaginative, and scientifically stimulating, but without the empirical proof required to move from speculation into accepted history. Future research into the Silurian hypothesis will require a systematic and methodical approach if it is to move from an intriguing idea to a scientifically testable framework. One of the most promising proposals involves deep core drilling into ancient sediment layers. Current geological sampling often focuses on relatively young strata, hundreds of thousands or a few million years old, but the Silurian hypothesis demands we examine much older deposits, perhaps tens or even hundreds of millions of years in age. The aim would be to locate chemical, isotopic, or structural anomalies that do not match any known natural process. If such anomalies are found, they could represent a form of technosignature preserved in Earth's geological record. The challenge is that deep core drilling is resource-intensive and technically demanding, often requiring highly specialized equipment to extract undisturbed cores from great depths while preserving delicate chemical and structural details. Chemical fingerprint analysis is another cornerstone of the research strategy. Advanced civilizations, as we know from our own industrial footprint, inevitably leave behind chemical markers that differ from natural geological compositions. For instance, isotopic ratios can be altered by industrial-scale processes, such as large-scale metal refinement, nuclear activity, or the creation of synthetic materials that do not occur naturally. Detecting unusual isotopic distributions in ancient sediments could provide a clue that industrial activity once occurred. Similarly, the discovery of synthetic compounds, plastics, complex polymers, or chemically stable dyes would be strong evidence of an advanced civilization, as such substances require deliberate engineering and do not arise spontaneously in nature. However, because geological and chemical processes can sometimes mimic artificial patterns, the interpretation of these findings will require extraordinary caution and rigorous peer review. The pursuit of such evidence cannot be limited to a single field of study. This is where interdisciplinary collaboration becomes essential. Geologists can identify target strata and assess geological transformations over millions of years. Archaeologists can offer expertise on how material culture degrades and what preservation environments might be favorable for survival over deep time. Climatologists can model how ancient atmospheric changes might record the fingerprints of industrial activity. Astrobiologists, drawing on knowledge of planetary habitability and extraterrestrial technosignatures, can help develop strategies to search for similar evidence, not only on Earth but also on Mars, Venus, or icy moons like Europa. By combining these perspectives, researchers can develop a more robust methodology for recognizing the signs of both past and potential future civilizations. The implications of this work extend far beyond pure academic interest. Understanding how an advanced civilization might collapse and how its traces might vanish has direct relevance to planetary defense and sustainability. If we can model the pathways through which industrial activity destabilizes climate systems or depletes critical resources, we gain a clearer understanding of how to avoid repeating such mistakes ourselves. Furthermore, studying the potential disappearance of prior civilizations could inform our strategies for managing Earth's resources, mitigating climate change, and reducing existential risks. This perspective shifts the Silurian hypothesis from a speculative exercise into a tool for long-term planetary stewardship. There is also a clear connection to the broader search for life in the universe. The techniques developed to investigate Earth's ancient strata could be applied to other planets. For example, a drill on Mars could extract deep cores from ancient lakebeds, searching for unusual isotopic ratios or synthetic materials that may have survived from a Martian industrial era, if one ever existed. The search for such technosignatures could complement the more traditional search for biosignatures, expanding our ability to detect both living and extinct civilizations. Silurian hypothesis, whether or not it is ever proven true, teaches us critical lessons about planetary fragility, sustainability, and humanity's place in the broader cosmic timeline. Even if no pre-human civilization ever existed, the act of searching forces us to confront the reality that Earth's biosphere is finite, that our industrial footprint may be far less permanent than we imagine, and that civilizations might be far more ephemeral than we wish to believe. These realizations have strategic importance, not just for science, but for policy, environmental management, and our vision of humanity's future among the stars. Under this view, the Silurian hypothesis takes on a dual role. On one hand, it is a stark reminder that even the most advanced civilization is not immune to the slow but relentless processes of geological change, climate instability, and the passage of deep time. Every road, tower, machine, and archive that defines a civilization's presence is ultimately subject to erosion, tectonic shifts, and chemical breakdown. Over spans of millions of years, entire continents drift, mountain ranges rise and fall, and seas advance and retreat. In that constant reshaping of the planet's surface, the evidence of a civilization can be obliterated, leaving little more than obscure chemical signals buried in strata no human eye may ever see again. This idea forces us to reflect on the fragility of our own presence on Earth. It suggests that permanence, at least in physical form, is an illusion, and that our greatest achievements may one day be reduced to traces too subtle for any future species to recognize. At the same time, the hypothesis also serves as a powerful source of inspiration. If it is possible for a civilization to leave such faint echoes that they remain hidden for tens or hundreds of millions of years, then there is a challenge before us: to consciously decide what kind of legacy we want to leave behind and how we can ensure that it survives the test of time. This isn't merely a question of creating monuments or storing data in more durable formats. It is a question of whether we can maintain a civilization stable enough to persist and evolve for time frames that far exceed recorded history. It pushes us to think beyond the next century, beyond the next millennium, into the realm of geological epochs where survival depends not on technological brilliance alone, but on our capacity to manage our planet's resources, climates, and ecosystems in ways that do not lead to collapse. When proponents speak of safeguarding our legacy, they are not imagining future archaeologists stumbling across a perfectly preserved city. Rather, they are thinking in terms of signals that might persist in the chemical and isotopic records, artificial compounds, unusual ratios of carbon isotopes, or stratigraphic layers that reveal sudden shifts in biodiversity or atmospheric composition. Our plastic pollution, for instance, is already embedding itself into the geological record, forming plastglomerates, rock-like substances made of sediment fused with melted plastic that could endure for millions of years. Our nuclear activities have left radionuclide signatures that will remain detectable far into the future. These are the kinds of traces that another civilization, returning to Earth after millions of years or emerging anew, might detect and use to piece together the fact that an intelligent industrial society once thrived here. The practical next steps suggested by this perspective, deep drilling into ancient sediments, applying advanced chemical analysis to rock cores, and fostering collaboration between disciplines, are not simply academic exercises. They have immediate relevance to the way we think about planetary stewardship today. By looking for the most subtle and long-lasting markers of industrial activity in Earth's geological past, we inevitably gain insights into how our own activities will be recorded in the future. This could help us better understand the consequences of our environmental impact and, in turn, inform strategies for mitigating the risks that threaten our long-term survival. Studying the persistence of synthetic chemicals, for example, might highlight the dangers of producing materials that are resistant to natural breakdown processes. Similarly, examining how fossil fuel combustion alters carbon isotope ratios over time could reinforce the urgency of transitioning to sustainable energy sources. These investigations also extend far beyond Earth. The Silurian Hypothesis is not only about the possibility of past civilizations here. It is about learning how to search for signs of life and intelligence elsewhere in the universe. If advanced societies are prone to collapsing and disappearing from the visible record in a geologically brief span, then our odds of detecting them while they are active may be slim. But if we learn to recognize the persistent subtle markers they leave behind, chemical anomalies in an atmosphere, for example, or unusual mineral deposits on a planetary surface, then we might still detect their existence long after they have gone. This approach mirrors the way paleontologists reconstruct entire species from a few fragments of bone. In the same way, astrobiologists might reconstruct the existence of a technological society from a handful of scattered planetary signatures. Thinking in these terms requires humility. It forces us to accept that we may not be the first intelligent beings to walk this Earth, and that our reign, however grand it feels in the present moment, could be as fleeting as any other. It also challenges the assumption that intelligence and technology necessarily guarantee permanence. The fossil record teaches us that dominant species can vanish quickly in geological terms, often due to environmental changes they did not foresee or could not adapt to. If this is true for us, then the lesson is not that civilization is pointless, but that survival depends on a delicate balance between technological progress and ecological stability. One of the most sobering aspects of this idea is the realization that the traces we leave might not be enough to tell our full story. A future intelligence might detect elevated levels of certain metals in the geological record, but they might not know whether those anomalies were the result of industrial mining, volcanic activity, or asteroid impacts. They might detect a spike in atmospheric CO2, but be unable to determine whether it was caused by fossil fuel combustion or by some natural feedback loop in Earth's climate system. Even if they detected radioactive isotopes from our nuclear age, the meaning of that signal could be open to interpretation. In this way, the hypothesis not only inspires us to search more carefully for traces of others, it also reminds us that much of history, especially on the scale of millions of years, may remain unknowable. This is where the warning aspect becomes clearest. If we wish to leave an unambiguous record of our existence, we must be intentional about it. This could mean developing methods of preservation that withstand geological upheaval, perhaps storing artifacts in geologically stable locations far underground, or embedding symbolic information into materials designed to last for tens of millions of years. It could also mean ensuring that the civilization itself survives long enough to continually pass on its knowledge, avoiding the collapse that would force future beings to reconstruct us from scraps. The fact that we can even discuss such possibilities is a testament to our scientific foresight, but the execution of these ideas would require unprecedented global coordination and commitment. Equally important, the hypothesis reframes the way we think about our place in the galaxy. If civilizations are inherently fragile and prone to vanishing, then the cosmos may be littered with planets that once hosted thriving societies, now reduced to nothing more than chemical imprints in stone. In that context, our survival becomes not just a matter of national or even planetary pride. It becomes a rare and precious opportunity to defy the odds and extend our presence into deep time. The responsibility is immense, because failure would not only mean the end of our own story, but also the loss of a potentially unique opportunity for intelligence to endure in this part of the universe. To act on this understanding, the next steps must be taken with both curiosity and urgency. Deep core drilling programs could target unexplored sections of Earth's crust, particularly those corresponding to unexplained climate events or mass extinctions in the geological record. Sophisticated isotope analysis could be applied to ancient rock layers to search for signals that cannot be explained by known natural processes. Collaboration between geologists, archaeologists, climatologists, and astrobiologists could merge expertise in ways that allow subtle evidence to be detected and correctly interpreted. These efforts would not only test the Silurian hypothesis, but also expand our knowledge of Earth's deep history in general, revealing patterns and processes that could inform everything from climate policy to space exploration. The true value of the Silurian hypothesis lies not in whether it is ultimately proven right or wrong, but in the perspective it offers. It teaches us to see civilization in the context of planetary time, where even the mightiest achievements are temporary unless they are sustained across unimaginable spans. It encourages us to think of survival as a long-term project, requiring not just technological sophistication, but also restraint, foresight, and a commitment to planetary stewardship. And it urges us to look both backward into the deep past, where others might have walked before us, and forward into the future, where our own traces will one day lie buried, awaiting discovery. In the end, the Silurian hypothesis challenges us to see ourselves not just as a moment in time, but as part of a vast unfolding planetary story. It asks us to think beyond the fleeting span of human history and to consider how our choices today will echo in the rocks, the oceans, and the skies millions of years from now. Whether or not a pre-human civilization ever walked this earth, the real question is what legacy we will leave behind, and whether it will be a tale of resilience or a cautionary relic of collapse. If we take its lesson to heart, perhaps our own civilization can endure long enough to be remembered not as a mystery to be solved, but as a triumph of foresight, adaptation, and unity. Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday where we unravel the darkest mysteries of space.